What I want to talk about today is periodic functions. First, real formal definition of a periodic function. Periodic function is function f but such that there exists a p where f of x plus p equals f of x for all x in the domain of f. Now, the book would call p the period of the function, and I'm going to make a distinction. P is a period of the function. The reason I say that is, if this is true, then f of x plus p equals f of x plus p, which of course equals f of x, which means that 2p is also a period, or 3 or 4, np. So specifically, I'm going to say, p is, period of the function is the smallest such p. That is what I'm going to call the period of the function, the smallest such p. Okay, let's talk about some examples in the real world where a mathematical periodic function would be a good model. Time on clock. It's 5 o'clock today, 5 p.m. today. Wait 24 hours, it's 5 p.m. again, on and on. We're going to find most of the examples of periodic functions we're going to look at are going to be time-based, but that's not the only possibility. You could say the ocean tides. Anyone know what the period of the ocean tides is? Does anyone know what causes the ocean tides? Yes. It is gravity. Whose gravity?
The moon.
The moon's gravity, yeah. Well, the Earth's gravity doesn't go away. It's just the moon's gravity. The moon would just suck all the ocean water and everything, right? But just raises it and lowers it a few feet. And the moon going around the Earth is about every 28 days. So even though at a particular point the water goes up and down about every 24 hours, it actually cycles, and the real cycle is every 25, about every 28 days. Okay. Now I know everyone's a little bit familiar with trigonometry, so let's start by looking at some periodic functions, the sine and the cosine. You've probably seen these before. These are sometimes called sinusoids. sinusoidal functions. One interesting thing we're going to, we will explore at some point is the fact that these two look almost identical. They just seem shifted. It's a horizontal shift. We'll find out that's true. Also, you can see there's a tangent function here. It's also periodic. Oh, I guess I should say the sine and cosine function, they go through a complete cycle every 360 degrees. The tangent function goes through a cycle every 180 degrees. It's also, should note that every 180 degrees there's a point that's undefined. Well, remember I said this is true for all x in the domain, so that's okay. It's okay if you have a periodic hole in your function that way. I don't know if any of you are interested in electronics, but often in electronics we hook up our oscilloscope to some electronic thing we're monitoring, and we find one of a number of these different periodic functions. Square wave is, everyone here has a computer, so everyone here has heard that your computer goes at a gigahertz or 2 gigahertz or something. So what's happening at a gigahertz? A gigahertz is not the period. A gigahertz is the frequency, which we're going to look at in a second. It's the reciprocal. But your computer will have what's called a clock. Clock is just a voltage that goes up and down. Typically, it's a square wave, and the frequency. Well, that's your clock. It's a square wave. These are other kinds of signals you'll sometimes see in electronics. I guess I want to mention something about the square wave because there's something a little disingenuous about that. What we've drawn up there really isn't a function, right? It is kind of a real-world thing, though. A real square wave would look like this, maybe. In other words, we just jump between these values. A real piece of electronics is going to take a finite amount of time to kind of drop down. So, again, these aren't, in the real world, you don't have a pure square wave. But these are periodic functions. They repeat with some period. Here's an example from astronomy. So you go out on a clear night, the right time of the year. You'll see there's this really bright star that isn't a star at all. It's the brightest thing that looks like a star. It's Jupiter. And if you look at it with a pair of binoculars, you'll see a little disk. And then you might see 2 or 3 or even 4 little bright lights on either side of it. They're the moons going around. And if you were to go out every few hours, every few days, and graph it, you'd see that the moons each go around Jupiter with their own period. So this is a good example of each of them is a periodic function. You'll notice also that the periods don't really match up in a nice way. Sometimes they do for physical reasons, but not with Jupiter, to my knowledge. Here's another example from astronomy. If you look up at the sun, there'll sometimes be these dark spots. And if you count them and you graph them for a long, long time, you find that depending upon how you want to treat it, is either an 11-year cycle or a 22-year cycle. Sunspots are caused by magnetic fields in the sun that change, and every 11 years the direction of the north and south pole of these fields switches. So the complete cycle is kind of 22 years, but you might not see that if you don't actually look at the magnetic field. This isn't a real tight kind of periodic function. This is just kind of if you look at the average number of sunspots and you watch it. Even this diagram, it's not that obvious, but there's a peak over here in 1779. It's kind of old data. And a peak over here. Oh, I'm sorry. It's these little guys are the cycles. And it looks like there's, within that cycle, there's kind of a longer term cycle too. I missed that the first time. Okay. There's something else going on with the sun, but I don't know what that is. Why are the peaks growing and decreasing over time? All right. So last real, well, you already did this, but you already mentioned this, but the tides are periodic. This is just some data from a spot in New York. And, you know, again, there's a little variation, but you can see over a 24-hour period approximately you get a peak and a trough, and then there's kind of a longer term period having to do with the moon going around the Earth. Oh, I'm sorry. We have one other example. This is a real important example. I don't know if this will download in a reasonable amount of time. Sound waves are periodic functions. When you hear a sound, it's really air pressure repeating. Yeah. I guess I'm going to stop that. I have a short little instructional video you can look at on sound waves. So let's see here.
Sets the air next to it in motion, alternately compressing and expanding it with each vibration. The variation of sound pressure can be detected not just with your ear, but also with a microphone connected to an oscilloscope that traces out a sine wave, showing how the sound pressure varies with time. We can also make sine waves with an electronic synthesizer. The number of vibrations per second is called the frequency. It's related to the sound or tone. For example, this tone has a frequency of 440 vibrations per second. Here's what happens if you double the frequency. The new sound, an octave higher, is called an overtone. And here's what it sounds like if you cut the frequency in half. The new sound is an octave lower. The height of the curve, up or down, depends on the loudness or intensity of the sound. The maximum height of the curve above the axis is called its amplitude. These examples show changes in amplitude for a given frequency. More complex sounds can be made by combining sine waves. For example, if you combine this tone with this overtone, the graph of the combination is obtained by adding the corresponding heights of the two sine curves. It sounds like this.
here? Playing instruments, or? Okay, so you know, you've heard of set thirds and fourths, right, and seconds, right? Which sound nice, and when the notes are right next to each other, they don't sound very nice. Well, thirds and fourths have this property that their overtones, the higher frequencies, match. So, just, did you know that?
Not until now. Not until now.
Not until now, yeah. Yeah, okay. And, you can have two instruments that are playing the same note, but they sound really differently because the primary frequency is the same, but all these overtones sound very different. And actually, pure tones like this, they kind of sound pure, but they're not very nice. Typically you wouldn't want to listen to some piece played with pure sine waves. It would be, I find it irritating. But okay, before we go on, we want some terminology for periodic functions. The video mentioned the amplitude, and we define the amplitude of a periodic function as the maximum minus the minimum over 2. So, for example, in the sine waves he was demonstrating, this was like the max and this is the min. Well, you take the difference and you divide by 2, and that would be the amplitude. Also, when we're dealing with things that are based in time, we have a synonym for period that I guess we've already been using. It's called a cycle. So you'll hear some frequency is 50 cycles per second. I'm sorry, that's a synonym for frequency. Excuse me. And we have frequency is just 1 over the period. They're reciprocals. Another feature of periodic functions, it's no different from any other function, is they will have a range. This is really different. This is different from the amplitude in a couple ways. You can have, say, a sine wave like this, and its amplitude might be this distance here, but its range is just this range of values. Also, I guess it's worth noting that go back to the tangent function, and this really, the range is all real numbers, so of course its amplitude is infinite. Okay, that's it. That's it for periodic functions right now. Are there any questions? Again, I wanted to develop a little terminology because we're gonna look at some periodic functions during in this next section. Right. I found out in the last class something. It was a little surprise. The surprise was most of my students here don't remember their geometry very well. So I think rather than run into it headlong, I'm going to just do a short little review of things from geometry you should know. Really, we're going to talk about triangle trigonometry, so we want to just go over a few things about triangles. Hope everyone remembers what a triangle is. It's a geometric object made up of 3 segments, 1, 2, 3, and of course there are 3 angles. Does everyone know what I mean by this notation where I put little marks here? Okay, good. We have a few theorems that describe, when 2 triangles are congruent. I say congruent because if we were to say they were equal, that would mean they're the same triangle. But congruent just means their 6 parts are all the same. So we have some theorems that tell us how we can know 2 triangles are congruent without having to know all 6 parts are the same. Does anyone remember any of those theorems? No. Well, they all have letters. That's not it. I don't know why I keep wanting to write that. First one is usually side, side, side. Does anyone remember what that theorem tells us? Gosh, okay. I'm glad I'm doing the review now. If 2 triangles each have 3 congruent sides, they're congruent. In other words, just knowing that the 3 sides are equal tells you that the angles are also equal. They're coming back to anyone? Yeah. There's a few other such theorems. There's side, angle, side. That tells me if I know that two triangles have 2 sides and an included angle congruent. That's all you need to know. The whole triangle has to be congruent. It's called side, angle, side. We also have angle, side, angle, which tells me something equivalent, only here if I have 2 angles and 1 side congruent, then I know they're congruent. Do you remember any of these? This is real basic. Okay, I saw one head, yes. 1 person. Okay. There's one more. It's letters, but it doesn't have 3 letters. It only has 2 letters, and they're not A and S. Does anyone want to venture a guess? Okay, it's called HL. Does anyone call HL? HL theorem? No. I have a right triangle. I call the long side the hypotenuse. And each of these other sides are called legs. There's a leg, here's a leg. HL says that if I have two triangles, their hypotenusae, plural of hypotenuse, their hypotenuses are congruent, and one of the legs is congruent. Well, they're a right triangle, so we know the right angle has to be congruent. Then they're congruent. And this is kind of part of the basics of triangle trigonometry. Let's go right to it. So, if you have a right triangle and it has a hypotenuse, and we're gonna be looking at this angle here, theta. It's the Greek letter theta. Is that our first? No, we use pi. Any other Greek letters? Yes. And I give the other legs names. I give the leg opposite from theta the name opposite, O for opposite, and the leg adjacent, I give the letter A. Then we define some functions based on those lengths. This is triangle trigonometry. We define the sine of theta as the opposite over the hypotenuse. We define the cosine of theta as the adjacent over the hypotenuse. And we define the tangent as the opposite over the adjacent. Now, those relationships are probably the most important things to remember. And so I'm going to present a memory device that I learned long after I went to high school trig class, but I think it's a good one. It goes like this. It's the mnemonic. So, it sounds like American Indian kind of language. Sounds like. What does it stand for? So, toa. Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Okay, that's the memory device. I want to note that this only works, this definition of these functions only work on a right triangle where my theta is less than 90 degrees and greater than 0 degrees. We don't have, if we have theta 0 degrees, we don't really have a triangle. And if we let theta grow and theta becomes 90 degrees, then we have two right triangles, and what do we know about these two segments? We have two 90-degree angles. What do we get then? If I seem to be expressing some disappointment, it's not in you. It's in teaching of mathematics in high schools. Okay. All right. So with this as our background, they're all different kinds of problems related to right triangles where we have some limited amount of information. I'm going to go back to my review for just a minute, because I think there's just one or two things that will come in handy. Does anyone recall what a triangle that has 3 equal sides is called?
Equilateral.
Equilateral, okay. And what do we know about the angles of an equilateral triangle? That was the answer to 2 questions. First question was, they're all equal, and then what are they? But thank you. They're all 60 degrees. Very good. Come back to this in a second. Does anyone recall what an isosceles triangle is? Isosceles, yes.
2 sides are equal.
2 sides are equal.
So 2 angles.
The opposite angles have to be equal. Yeah. So if I have a right triangle, and it happens to be isosceles, it's got a right triangle. I know these angles are the same, but what are they?
45.
They're 45. Now, it's Alexis, right? How do you know it's 45?
Because triangles, the angles within them have to equal 180.
Yeah, 45 plus 45 plus 90 have to equal 180. Okay, good. Going back to the 60-degree triangle, I want to show you something you may have seen. You really want to keep this in mind. I can drop an altitude from the vertex here. An altitude is a line that's perpendicular to this side. So I have 2 right triangles here. The hypotenusi are the same because equilateral triangle, all the sides are the same. This leg has to be the same because it's the same segment. Right? So I have hypotenuse leg. It tells me these 2 triangles are congruent. They have the same parts. If they have the same parts, then these angles have to be congruent, and they have to add up to 60 degrees. So therefore, they have to have how many degrees? 30, right. So that gives us some insight into the 30, 60, 90 triangle. We know that these 2 legs, the length of these 2 legs adds up to the entire length of the leg, of the side, which is to say each of these sides is 1/2 the hypotenuse, right? This is the hypotenuse. So I know in a 30, 60, 90 triangle, the shorter leg is half the length of the hypotenuse. We're going to find the last leg. The famous theorem named after Pythagoras. Am I going to use? I can't go any further than that. It's the Pythagorean theorem, right? So it's going to be 1/2 h squared, square root of h squared plus 1/2 h squared. What's that going to be? Not 1/2 h squared, but 1/4 h squared. No, it's not. I have to subtract. So it's the square root of h squared times 3/4, or square root of 3 h over 2. Is that right? Yeah. So in a 30-60 right triangle, you have sides h, half of h, and square root of 3h over 2. I don't know how you get past the 500 on the SATs without knowing that. I'm sure many of you did, so. Okay. Want this over there. All right, back to trigonometry. So I have a problem here. I have a right triangle. The angle here is 60 degrees, and the length of the side is 10. And I want to find the other parts of this triangle. So how do I do that? Well, this angle, I think we already know, right? That's 30 degrees. We decided that this side was 5. And so then this is 5 times the square root of 3 over 2. So I can look at this and I can extract some useful trigonometric information. I know that the sine of 60 degrees is what? Well, the opposite over the hypotenuse. So 5/2 square root of 3 over 10 is what? I don't think I did that right. I did something wrong here. This is 5 times the square root of 3. So 5 over 10 times the square root of 3 is just the square root of 3 over 2. The cosine is even easier. That's just 5 over 10. And the tangent function will just be the sine over the cosine, or the opposite over the hypotenuse, which is 5 square root of 3 over 5, which is square root of 3. All right, that's very nice. We just know a little tiny bit of trigonometry. What would be really useful is if we knew the sines, cosines, and tangents of all the angles, right, between 0 and 90 degrees. Well, for that, we have some technology. Well, it's not in here. Okay, we have looks like a TI-82 computer, a little behind the times here. You'll notice over here there's buttons, sine, cosine, and tangent. Well, that's great. We can find out the value of these functions just by punching them in. We do have to be a little careful right now. Does anyone recognize the screen I'm on above here? Does anyone know what this is? Anyone recognize the screen, my calculator? It's a mode screen, right? If you hit the mode button. The reason I mention this is the most common error I find students make in doing trigonometry with their calculator is they're in the wrong mode. If you have a different brand, you still probably have to take a look. You'll notice over here it says radian or degree. While we're using degrees, we want to be in degree mode. If you're in the wrong mode, you're going to get very weird answers that are going to be wrong. But anyway, you put your calculator in the right mode, and then you can just punch in a number here. We didn't always have calculators to rely on this way. Instead, kind of like those, I think I showed you the log tables a while ago. We had books filled with log tables. This is just one page showing various functions, sine and cosine. And I think this is just the 2-degree page. You may notice that, you know, we'll see why this is later, but there are other degrees listed up here, but the only degree between 0 and 90 is 2 degrees. Okay. Well, before we do a real problem, I just want to mention, since we figured out the sines and cosines of 60-degree triangles, well, let's just take a second here, look at a 30-degree, this here, 30-degree triangle. Here the opposite and the adjacent are switched, but that's all. So the sine of 30 degrees is going to equal 1/2. The cosine will be the square root of 3 over 2. Some people can't really see over this one. And then the tangent is just reciprocal. One over the square root of 3. There's another triangle we can figure out these values for. It's actually a little easier. If I have an isosceles right triangle, and I know the angles are 45 degrees, and the sides are 1 square root of 2. So the sine of 45 degrees we know is 1 square root of 2. The cosine is the same, and then the tangent is just going to be sine over cosine of 1. But now let's look at a real problem where we don't have a nice angle. Or at least we don't know we have a nice angle. If I had a triangle whose sides, a right triangle whose sides are 4 and 10, well, what can I say about this triangle? You know, the cosine of theta is what? Cosine is the opposite over the hypotenuse. Yes, Penny?
Oh. 4, I would say 4 over 10.
Sorry?
It would be like 4 over 10.
This is 4 over 10, yeah. 0.4. Okay. Well, what good does that do us? Let's go look back at our calculator for a second. Okay, look down here near the cosine function. You see in the little blue letters, inverse cosine function? Aha! So we plug in inverse cosine of 0.4, and what do we get? Somebody. I am so glad you said that. Beta equals 1.16, is that right? Okay. What did I say was the most important thing to do when you're using this? Get it in the right mode. This is the right answer, it's just not in degrees, it's in radians. Someone want to try it using degrees instead of radians? 66.442 degrees, yeah. Okay, so I know 66.42 degrees. The rest is easy. The rest of this triangle is easy. This angle here is what? This is a complementary angle. Remember complementary angles? So it's just 90 minus 66.42, which is 23, 23.58. What about this third side here? How can I find that? Pythagorean theorem, right. So that's going to be 100, 10 squared minus 16, square root of it. Okay, we're gonna do more with this, but I just want to kind of get the basics down. Again, hypotenuse leg tells me that once I have a hypotenuse and a leg, right? That triangle is determined and I can find all its parts. I just don't have a way with geometry to find it. I need these functions, these sines and cosine functions. There's something else I want to say, but I'm not quite sure. Yes, I've run out of things to say. Okay, thank you. Again, the first part of the homework assignment will go up, but it's not going to be due till a week from today. So don't worry too much about it. Don't worry about the exam. Prepare for the exam on Monday. And again, if you want to see me, I'll be in